So I already posted the homework to the canvas. Then we got 1.5 weeks to finish them. So the homework assignment only have 5 questions, quite a simple one. They're really similar to the tutorial and also to the lab. So I don't think there will be any problem. If any problem, come to see me. So today we continue to discuss about the transformer. So let's go through really quickly about what we had done last 2 days ago. So we talk about the matching, how the transformer can be used on matching devices. Because you can see then here, then if we do any impedance through a transformer, we can change the impedance when we view the transformer from the other side of the transformer. For instance, if we connect transformer in the secondary side right in here, then on the primary side, we can see the transformer becomes some impedance related to the transformer turns ratio. That's one of the ways we can adjust the transformer. The detailed equation will be here. So this method has been used quite often in order to do the transformer impedance matching, like in the speaker or maximum power transfer. We always know that if you want to have maximum power transfer, we usually need to adjust the impedance. For instance, many systems, they say if the low resistance like that, and the transmission in source impedance is another one, if these two are equal, we're able to have our optimum best power transfer. So that's one of the ways we can use transformer to do the job. So here will be example. I showed you last week. If you want to get the current in here, instead to get the potential here will be really complicated. And then we can refer all the components using the transformer, refer to the primary side, because that's kind of the impedance. And then we can just using a single loop to get the current, and then you can get the voltage quite straightforward. So one of the advantage, if there's a transformer circuitry, how we work out. So that's how we work out the impedance, and then we can work out the current in the circuit, and then we can work out the voltage on the other side of the transformer. Another interesting point, we can see that here will be transformer connection. You see, sometimes we have been given with maybe 1 or 2 or 3 transformers, we found a way how to put them together. So in this case, you can see that if in here, if we're putting 2 transformers in parallel, exactly parallel, if the 2 transformers are identical, equal to each other, you can just parallel them. So for instance, if this transformer is same turn ratio, same kind of number of turns, same kind of the magnetic core, we can just parallel them up. But of course, one thing we noticed that will be no transformer, no component can be identical. They may be slightly different by 1%, 0.1%. So that is to say, in parallel side here, if you connect them in parallel, of course, we'll impress the same voltage on the primary side. But in the secondary side in here, maybe slightly different in the voltage, maybe different by 1%, 0.1%, whatever. But if you connect them up, then we end up with something, an equal voltage putting together. What do you like this?
I'd imagine that if you successfully connect the transformers in parallel, it increases the current capacity of the transformer.
Yeah.
Is there any other way to do it other than this?
There's many ways to do that.
I see.
In the next slide, we are going to show you many different ways to connect transformer.
Okay.
So many of the methods will be more logical, safer. This method is not safe method.
Yeah.
Only something I showed you the possible connection. Doesn't mean you have to do it. I won't use this method. I never use this method. Why? As I mentioned before, no 2 transformers can be identical. If you connect 2 different things together, you scare about some kind of the unequal voltage connection. Just like 2 batteries. This battery cell A battery 1.5, this also 1.5. In 3, we connect them in parallel, we're able to double the power. But however, problem coming to this may be slightly different by 1%. And will be this voltage will try to charge up or deliver additional current to the unit. You will losing out some energy. That's called the circulating current. For instance, why something here much big? You can see that this battery, right? You can connect this 1.1 ohm. So this another battery will be another 1.5 volt. and then we try to connect to a load. So using two branch array, we can able to double the power, double the current. But however, if this is 1.51, end up will be, you see, because some internal resistance here, some circuiting current will looking in here, raising some energy. Of course, if they exactly equal voltage, you don't have any problem. But nothing can be identical, exactly equal. Some changing. So that's why, in theory, we can connect two transformers in such a way, but that's only the possible connection. So I don't do that, but just for teaching, I show you it's possible. So if the two transformer connected in this parallel, then of course we can double the power or double the current. And then you can see turn ratio still the same, still N2 over N1. But the problem is there may be some internal circulation, like in here. Circulation here, you're losing some energy, reducing the efficiency. There's something we need to be careful about that. All right. So there's another better way to connect will be we can use this method to prevent some internal circulation. You can see in here. So with primary side, we are trying to parallel them, but secondary side we put them in series. So it more look like we double the output voltage. So you can write down the transformer equation here. For the output voltage will be input multiplied by the turns ratio plus the another output here, which is V in multiplied by turns ratio. We can see that the voltage being enlarged, doubled. Yes?
And would this affect the current in any way, or would that just be the exact same?
What do you think? What kind of parameter you are better? Certainly, the voltage will be doubled, right?
So
But the current will be the same. Output current will be unchanged. Because the transformer is now connected in series. So that means when series connection, each transformer contribute to its own current. So the output current is unchanged, but the voltage being doubled. Of course, you can see that the voltage double, current unchanged, then the power will also, total power become double. Yeah. So, but that's the way is a better connection because in the output side, there won't be any circulating current. Like in here, we parallel, then we may have circulating current. But if you these two batteries, we connect them in this one. 1.5, 1.51. Of course, it's not really double the voltage. The current is unchanged. This current, but there won't be any circulating current forming between these two because we add up the voltage. This is some kind of analogy. You can see that from the transformer, we are able to double the voltage, but under the same current condition. So that's another possible connection. We can therefore increase the voltage. That is to say, in some case, if you transformer, you are outputting say 120 volts. But in a way you want to move the transformer to operate in other countries, they require 240. You can put two transformers in parallel in this way. That is safe to do because you don't have to worry about the circulating current. This is a better way to do that. Okay. So this already, but so I call it PS parallel in primary side and series in the secondary side. And then two transformer, of course, they have 2 by 2. We got 4 possible combination. And the combination will be like that. So now then we have series in the input side, and then we'll parallel in the output side. Obviously, you can see that, again, we input all the parameters in here. Output voltage will be the same Vout. Input voltage here, we are using reverse conversion ratio. So output multiplied by this term ratio N1, N2, and then we end up with the voltage conversion ratio being half of the original. Yes?
Would the current increase in this
What
case?
do you think? Of course, that's the next question I'd like to ask you. You asked before me. So let me ask something. So will the input current being double or the same or decrease? What do you think? Input side. Anybody can put your hand? How about you answer?
Input
side. Look at either side. Input first.
No, but the output side was sensitive.
Yes. Input side in here you can see that connected in series. So then in current will be unchanged. The same transformer times on. So that's the thing. So this current will be the same. Second side is be parallel pull together, then we eventually look like double the current, increase the current. So this transformer configuration will be like that. If you want double the power, of course we have to use two transformers together. But in the key advantage of this one will be you can double the input voltage. For instance, you got transformer 120 in US, but move the transformer to use in Europe, the input voltage 240. If you don't have any component 240, you can use two transformer connect in series and use in the Europe. Then your transformer become input 240. That's the way you can do that.
Would that mean in the one before where it was parallel to series, would that mean that current would be halved?
Yeah, the basic concept will be really similar to say, for instance, if you want to look at this, the previous one, we are now parallel input, then of course the input current can be double. In here, the current output side in series is the same, but the voltage being double. So the concept is straightforward. Just look at the configurations. Some of them can be double, can be the same, can be we do have either, for this case, either double or the same, right? Okay. So that's the configuration in here for the series and parallel. So key application will be you can increase the voltage rating, the input side. So that's quite good because if you have transformer only have 120 volt, now you want to double the voltage rating in the input side, then that's one of the way you can do that. So you can see that by using the configuration, you can, in a way, you can use two transformer configurations. Sometime in US, sometime in Europe, you can have either 120 volt or 240 volt. The one of the way we can do using some connection of the transformer to do the job. So obviously another configuration is S and S. Yeah. So for series input, series output, obviously you can see that the input power, of course, must be double. We have two transformers. And then the voltage, we got two voltage here, add up together. Of course, the input will be double the voltage rating. And the current will be unchanged. And then on the output side, we also double the voltage. And current will be unchanged. Okay, so very straightforward. You can see that. I don't put down the phenomenon here. I think you can really easy to work out which one is double, which one is unchanged, right? Either input or output. So because we got two transformer, two times two, we got four configuration, possible configuration. So it's quite simple and straightforward. You're able to estimate it. One thing we noticed that will be in here, if we assume the two transformer connected in series, then if two transformers are identical, they should share the voltage equally. So the input voltage can be V in divided by 2. And the other transformer, V in divided by 2. So work out the conversion ratio N2 over N1 is the same conversion ratio. And then you come to another condition will be, because those transformers could be identical, they may not share the voltage exactly equal to each other. Then in this case, I try to work out if they don't share equally, I put a ratio A here. For instance, the winding V12 here only have an A ratio of the input voltage, for instance, 0.45. A can be 0.45, 0.4, 0.55, and the remaining one will be 1 minus. And then we put it into this equation, we also end up will be the same conversion ratio. That is to say for this configuration method, we don't need the input voltage exactly equal to each other in the primary side, or we don't need two transformers exactly equal. As long as they don't far away from each other, then when we connect them in primary side, even though their voltage in here is not balanced, they can still have same conversion ratio. So it's a nice thing to have. So that's why you can see that in here, we have been discussing with four topology, four connection method. The first one is not very reliable, depending on if the transformer is identical. Then if they are not exactly the same, we have some current, circulating current, additional power loss inside. But the other three topology, we don't have that problem. Even though they different by a little bit, by a few percent, we don't have any major issue. Yes?
Would primary series and or is it secondary parallel not much losses? I would expect it to.
Let's look at this to see any problem. Yeah. So you're talking about primary side will be in series, secondary side in parallel. You see in here, this side will be in parallel. So the transformer will transform voltage from the secondary side back to the primary side, right? So that is to say the transformer itself, they already control the output voltage will equal to each other. So when they transmit the voltage back to the primary side, we are not putting them in parallel, we put them in series. More look like we got primary side full battery connect in series and then connect to the input. So that means the circulating current between them will be negligible, will not be a big issue. Yeah.
So as long as one of the two sides has a series,
That usually will be safe. Yeah.
usually it's fine, okay.
Yeah. So that's a really good observation. We tend to reduce the circulating current and equal voltage put together. So we cannot have both sides parallel because that can be quite dangerous. We just look like shorting the voltage in such a way. But one side will be in series, will be good. That's the rule of thumb. So now then, after four topology discussion, you can know which one, they all double the power. But some of them will be increased in voltage, some of them will be increased in current, right? So you now should know which one is which, okay? Do you all get that? So this will be a really simple configuration. So next topic you may need to think at home will be how, if you got three transformers, how can I connect them in such a way parallel series? You can work them out. Three transformer, how to triple the power. Then the rule of thumb will be in series, usually will be safe. One side must be in series, the other side can be parallel, but don't have both sides parallel, will be quite dangerous. There's a basic law for this kind of the connection. Okay, so it's really interesting. At home, you can use at your own time to see you can able to connect a number of transformers in parallel series. If we give you four transformers, some of them can be parallel, some of them can be in series to work the power. Then you can sometimes increase the input voltage or increase the output voltage by putting some in parallel series. So this is, you try to play around with that. Could be quite interesting to do the job. That's the way we call it the topology. Topology is a way we can able to produce different combination of the connection. Then we can produce some new circuitry, new connection. So you can see that in the future, if you think about, if you got transformer here, got one transformer, you got three transformer. Of then, of course, if you want to triple the voltage, then you connect them in series. Outside, then we will therefore have a free output, independent output. That's another way to do that. Separate output. Because transformer point of view, you can able to have isolated output, free separate output. So that's the thing. But if the transformer are more identical, you can able to share the voltage equally. Yeah. So now then in 3V, you got 1/3 of V in, 1/3 of V in, 1/3 of V in. But how to make this free voltage are equal to each other depend on the transformer itself. If the transformer is not identical, may not able to share the voltage equally. And then you can see here, you can parallel in secondary side to triple the current. Or in this case, you can also series them In here, you can also free time the output if you like. So free transformer, you got more combination. You can perhaps 2 is parallel, 1 in series or whatever, but you need to think carefully, would there be any issue for circulating current? So case by case study, but that will be really interesting topic. And then if you extend to 4 transformer, 5 transformer, multiple n transformer, then you can find many combinations. Then you can help me to prepare a journal paper, a technical paper, stick to a conference or journal to see the universal combination of transformers. That can be very interesting analysis on. Okay? So don't think about that, how to combine n and n. So that gives you a really basic brainstorming how a transformer connection look like. This is really practical because we can use single transformer to deliver the various output current, various power rating, and also voltage rating. Especially we all have different voltage rating. Sometimes we need this power, double power, triple voltage. So it's very useful. Anyway. So next topic will be some other connection. Just now we discussed about all the transformer have the same conversion ratio, same turns ratio. But what happens if the transformer have different turns ratio? So you can see it here, if we're connecting 2 transformers in such a way, 1 to 3 and 1 to 2, right? Then let's see the conversion ratio. We now parallel the input and also in series with the output. So now then we can output with 3 times the input, twice of the input, then we have 5 times conversion ratio. So that's quite interesting. But bear in mind, last week we're discussing about the dot rotation. So that it means the polarity. If the dot rotation in such a way, we can therefore add up the output voltage, become 5 times. So that's the way we can connect the transformer. But now then, another way we can connect output side in series, we can see the dot rotation as now in here. So these 2 and these 2 will be in opposite polarity. We are now subtracting the voltage. So that's why I can see that in output, the conversion ratio here become 3 times the input minus 2 times the output. Right? So that's why our conversion become 1. Yes?
So just because of the polarity of the secondary side are one,
Yeah. That's
they're wasting 4/5 of the power.
That's a good point. For the conversion point of view or the connection point of view, we are creating 2 transformer. We are creating 2 possible voltage output. By we connect the transformer, maybe you can using relay to do the job. But of course, the disadvantage, like John mentioned just now, we now raising some kind of the transformer turns ratio. But why we still do that? The thing is, transformer efficiency usually 99% at least. You may raising a little bit percentage, become 98.5. But the advantage will be we have new combination. We can just using some relay transistor to create a new conversion ratio with a given transformer. You see, when we buy or procure a new transformer, also could be expensive. So that's one of the way we can have different combination. Yes?
What happens to the power? Can't just use power. Some of that energy has to go somewhere. So what happens to it? Does it
That's
get
a very good question. So for the second topology, what we can see there, you see the output voltage being less than before, right? What is the power? Will the power become still double, or the power will become something else? Can you calculate the power for the second circuit?
As long as the current's the same.
That's really good question observation. What is the power then?
Proportional to
But the first circuit, I'm sure the power will be double, right? Yeah, we want double summation of these 2 angles. But for this one, then the power could be Anyone can answer my question? What do you think? What do you think the power rating will be higher, lower, unchanged, and how much lower, how much higher?
On the expense, really not sure. How does this be similar?
One thing we observe that will be some voltage being cancelled out in here. So, and then the current, output current is unchanged. You get the same transformer, same second dividing. So that means the power level at the output side will be lower than expected. How much lower? Just simply calculate. Originally, you got 5 units in output, but now decreased to only 1 unit. The current is unchanged. So that means the power rating will decrease from 5 units to 1 unit, lose out 80% of power. That is the basic. That's a good point. Any other questions? So in here, we got a few scenarios to show you. One thing will be we are able to use transformer combination to develop a thinking for various voltage conversion ratio. Any two transformer, two type of ratio we can develop various output. And then we can also observe that power rating can be not really double, but can be diminished. So there's something we observe with it. So let's look at another way of combination. For the change transformer, but now that if you're putting them in another way. So we got two transformers again, 1 to 3 and 1 to 2. And now we connect the output side in parallel, the input side in series. And then we can also work out the voltage conversion ratio again. So the output in here will be unchanged anyway. Unchanged. The input side, because this output, we can use turn ratio to calculate how much the input will transform itself. They don't care about which one in or out. So now then output and then multiply half become this voltage. And output here multiplied by 1/3, we become this voltage. Add together we equal the input voltage. And the conversion ratio becomes 6/5. So now then you can see that the power will be the summation of these two because we are adding up the voltage. But however, the voltage conversion ratio now becomes 6/5. So we got a new conversion ratio using two transformers. So that's quite interesting. And then if you look at this case, we now reverse the dot rotation here. We reverse the dot rotation. So that means here we now can cancel out some voltage. So again, we got Vout times half in the input side, but this one, because we're reversing the voltage, then we minus Vout over 1/3. The conversion ratio here becomes 6. Okay. Yes?
Would the second one be affected by the A times B out or like then the 1 minus A thing?
No.
Or
Here you can see that the parallel.
Oh, it's parallel. Yeah,
So this
never mind.
will control the output anyway.
Yeah, no, that was the knowledge.
So the most important part will be if one side will be parallel, one side series, the usage will be safe, will be good circuitry. If not, then we need to think carefully, would there be any circuitry? So now then you can see that the voltage conversion ratio becomes 6. So next job you can think carefully would there be any power losing? Would that be the double power or losing some power? So in this case, you need to think about in the current direction, what will there be any current missing or voltage missing? But the conclusion here will be, we have only two transformers. We are able to create a various connection in here, 5, 1, 6/5, and 6 times. And together with the original rating 1 to 2 and 1 to 3, you can actually have 6 ways of connection, right? And then there's another way of connection, including each transformer we got ratio of 1 to 2. Each transformer we got ratio of 1 to 3. So add up together, we got many possible combinations. Okay. So you can see that now, if we got only a 2 transformer, we can have a number of them. So let's see how many we can generate. So that's right in here. We have 5. 1. What else you can think of course? That's 6 over 5, and also 6. And then together with the original one, then we can have 2, because 1 to 2, original one 3. Like that. And then we can revert the transformer. Front to back, back to front, then we can, of course, we can have another reverse it become, I think should be 1/5, 1/6, 1/6, 1/2, and 1/3. When we reverse that.
Then the second one wouldn't the second one have current that's just like circulating on the back?
It can be. Without any circulating current.
Happy things, so, right? Just
As I mentioned, usually if one side is in series, then we can restrict most of the circulating current, because we do not try to allow the current flowing from one winding to the other winding. So that's a rule of thumb how to make safe connection. You can see that we are now doing this input output. But so the total transformer ratio will be 6. But now if we input in here, then we just insert this voltage and this voltage in here. And the other side, we are now just using some kind of more cancellation of some money. And in this case, the current output they're in series. And this series current will reflect on here, become this current. This current will reflect in here, become this current based on the turns ratio. And then we adding these 2 currents to the sum. So that means if we check carefully, we don't have any circulating current. We don't have any wasting. But the disadvantage will be we are now canceling some of the number of turns here. So this more look like the scenario you see if we do have a transformer. If we transform here. So if we're doing like that, then we are good. But if we are not doing this, if we now reversing, doing this again, reverse, then of course we automatically cancel our own winding, because we're supposing all the winding will be same direction. If in the middle of winding you reverse direction for a few turns and back, you cancel some winding. So that is the similar thinking you cancel out some of the winding. So you can see that what this lecture is trying to show you will be, we do a number of ways to connect the transformer. And in here, this is some of the conversion ratio. And then with front to back, back to front, we've got a set of combinations. So, and then you can also connect in series, like 1 to 2 and 1 to 3, of course, will become 6 times. Right? So there's many ways to. So that is more look like parallel connection, but you can also have series connection. Some of the people, they may also connect to these things. One thing, and then if you got another 1 to 3. The whole one should 1 to 6. That's a very. So the equal point you can see here will be only 2 transformers. We are able to create many combinations, many voltage conversion with only different 2 components, but you are able to get many output, many scenarios. So more complicated than the battery one. So that's the interesting point. So this topic only about 2 transformers. about 1 to 2 and 1 to 4. You can see that if now I give you another exam question, 1 to 3 and 1 to 4, two transformer, how many combinations can it generate? That would be an interesting research topic or exam question, right? Yeah. You prepare for it, I put it in the exam. Yeah. Go home, try to write down all the possible combinations, and then provide to me in the exam paper.
Yeah, I was gonna say, how many transformers would we have? Like in the exam, unlimited amount of one different transformers.
Usually in the exam or in the quiz, only one transformer and maybe at most 3 transformers. I don't require, you see in here, we got 6 combinations plus the backside front, the 12 combination. So of course, I may not expecting you to have 12 combination. Maybe just write down a few combinations can have full mark.
Yeah.
That's the way I try to examine how you frame a problem. The first exam, I won't ask you this question. I may ask you 1 to 3, 1 to 4, maybe 1 to 5, 1 to 4, or whatever. But do prepare some simple combination, simple ratio first. I won't ask you 1 to 1.5 this kind of combination, but that's really interesting thinking. All right. Any question? Do you find this topic interesting? Yeah. Simple phenomena, but generally are not of the idea. That's the thing I like you to. Yeah.
Sorry, I wanna ask a question on how the for the what guys that parallel output, when you reverse the polarity of the other transformer output transformer on the bottom, how come the high voltage section of the both transformer doesn't short out to the low voltage section of the other one?
That's a really good question. A transformer is cell only at 2 set winding.
Yeah.
The cell don't really know which one will cause the division. You need to dot rotation here. Mean when they apply also here, will be reverse to the other side or vice versa. So in a way, I can move this dot in here, move this dot in here with the same transformer. The transformer actually they don't care what they don't know that themselves. So it's your own way to arrange it.
Okay, so is it less of like a voltage difference, more of like an EMF that's induced in the circuit?
Yeah.
Okay, that's helpful.
So that's a very good point. So that means if I want to reverse the polarity like this, okay, of course it can include like that. It's exactly the same. So even though these two dots same polarity, I can put both dots move to the bottom side. Is no change to the operation. Okay, you get that? These two dots remove all here, no change. If the transform itself isolated component, they don't care which one is 1 or 2, as long as stop rotation clear, that will do. Any other questions? So after this lecture, you'll become an expert in transformer, but only single phase transformer. So next half an hour, I will show you 3 phase transformer. That's another new area of the development. Anyway. So next thing also quite interesting about the auto transformer. Auto transformer doesn't mean the transformer is automatic, but usually a transformer will have 2 windings, primary side and secondary side. And in a way, if we want to reduce one winding, we can put a tapping in the primary side. They share the same magnetic core. Then in this case, we can simplify the transformer. The transversal principle is still there, but we just share this winding between the primary side and secondary side. So that's a really common transformer. If it's some application, we don't like to have the isolation, magnetic isolation, then we can use the same winding. Put in a tapping, that can do the same job. So like this sample with our auto transformer, we can turn this knob, we can control the tapping or control number of turns in the secondary side. You can change the voltage. Just like you are variable output transformers. This commonly available in many cases, but for most of the high power system with fixed transformer, but for some transformer, home use, or some industrial experiment, we can use automatic transformer, auto transformer to change the output connection. In this point, we move up and down like this and to access the output connection. So this is called the auto transformer. So auto transformer doesn't mean automatic, but allow you to change the output voltage. So the problem is you don't have any galvanic isolation because these wires are physically connected to this wire. But the good thing is we can reduce a separate winding in the secondary side. We share the same winding in the primary side. So that's the key message. So the conversion ratio will be just the same as before. V2 of V1 equal N2 over N1. I just use a name called 1 over N. Now, obviously, if the 1 over N, this one is less than 1, it will be a step-down transformer, just like here, step-down, or reverse will be step-up anyway. And the current ratio will be the same. So, but one thing we noticed that will be about the current in the shaded winding. You see, by using the Kirchhoff's law, if input current is I1, output current I2, so this current must be equal I1 minus I2, or reverse in this side will be I2 minus I1. So that is, in a way, you can see that this current, due to Kirchhoff's law, you can actually reduce the current, less current. Without thinking, you always think when you share a winding, probably you need to take care of primary side current and secondary side current. But in this case, due to Kirchhoff's law, we can see that some current cancel out. We have less current in the common winding here. Then I like to see the condition, this current, I2 minus I1, when will this current will be greater than the I1? There's some chance who can be greater because they step down. So the I1 current will be less than I2. You see all the step down transformer, input current will be less than output current. So that means input current is less current. We also know that the current cancellation here, we also less current. We just see which condition will be have less current in the common winding. By this inequality, we can just work out when num n equal to greater than 2, this current will be less than this current. So that is to say, when n is greater than 2, I can use less copper in here to save some investment, save some copper cost. But if the n is less than 2, then this current will become less. So that is this very simple inequality will tell you under what kind of parameter or n, the term ratio, will give you what is the requirement for the current in here. But anyway, we can see that we have capability to have less current in the shaded winding, can save some copper cost. So there's one observation we can see here. Another observation we can see will be for step-up transformer. Step up, like in here, you got more winding in the secondary side. Again, so that means the conversion ratio is the same, but when 1 over n, this whole parameter is greater than 1, of course, we'll step up. Yeah. My notation here will be 1 over n is our output to input conversion ratio. So again, I want to check the winding. This shared winding, right? So current is I1 minus I2. Output current is equal to I2. It's a step-up transformer. So output current is supposed to be less than input. And then I want to see, because this is less current, this is also has some cancel current. Then I want to see which one is smaller. Then the condition will be, let me check if when the N2 winding I1 minus I2 is greater than I2, what is the condition? Then that inequality can give us when n is less than half, less than 0.5. So in this case, then you can see that under that condition, if n is such a parameter, then we have a larger current in here. So that gives us thinking how we're going to design the transformer. I usually update my lecture notes every day. So your version may not be latest. Then if you want to get the latest version, you check our canvas. Yeah. That's one of the latest version. Yes.
So in a step up, there's more voltage and less current, correct?
Yeah.
Yes.
So you see the whole transformer. This is only a transformer, but it's common winding transformer. For transformer, then this input voltage conversion ratio is, we can use the term ratio to calculate about the current. So for step up transformer, we're going to have high current here, low current in outside.
Does that
So
mean,
that means this current will be lower. And
does that mean power is conserved?
the total power, the design transformer should be equal on both sides. Because it's the same kind of transformer.
So would this have less losses due to the transformer? Or would it still have around the similar amount of loss due to the transformer itself?
But you may be thinking about, would we have any unnecessary cancellation, losing some energy or power or voltage anything. So that's the key thing for the auto transformer design. We are now using the same magnetic core, putting one winding here, one winding to represent the input and output. So in this case, we don't actually, like the previous topology, we are losing out some number of turns. We are still using the necessary number of turns to create for us the voltage conversion. We don't lose anything. And then for all these transformers, the power input output are the same. That's how we design it. So the good thing of this transformer will be here will be a winding shared by input and output. Because the difference in the current direction, we are now able to cancel out some of the current. We actually have some benefit than the two winding transformer. Two winding transformer, each winding had to provide that amount of the output power or input power. But here, the transformer input and output also tend to provide the same output power or input power. But the winding itself is not the case. The winding being shared, but cancel out. So we are actually require less current in the shared winding. So this inequality I show you, we find that somewhat current being less than we expected. Either less than input or less than output depend on step up or step down. So that's a good advantage. So that means the major contribution in these two slides will be, you can see that the current being less than before. That is the major benefit. But of course, the auto transformer disadvantage will be, we don't have isolation. We don't have any magnetic isolation. But that's lower cost because you can see that we are now, we can able to use less copper, much less. And then we don't like the transformer sometimes with primary, secondary, then too many winding, then coupling the window to do the winding is really difficult. So this is a really simple design transformer, able to provide a number of advantages. So let's see a simple tutorial. Then you can tell you more information about how we understand the auto transformer. You see, auto transformer is really famous transformer in commercial market. Many people have been using it in the past. Probably you have used it in the lab. Sometime you want to adjust the input voltage, especially when you do the caption product. The input voltage 120 is a bit scary. You use 120. You first use auto transformer, start from 0 volt, 10 volt, 5 volt, 15 volt, gradually you increase the voltage until you're safe. Then you are competent. So that's how we do the caption project. So don't start with 120. Quite scary. So that's why many students tend to use the auto transformer. As long as well, sometimes if you're drawing too much current, the output voltage will drop due to the loading effect. Then you can adjust slightly with the load and increase the voltage. You have exact the voltage for your experiment. Anyway, here now we got an auto transformer, but the term ratio N1 to N3. Now you can see that 4,200. But if you say N1 to N2, will be the other termination. So input voltage will be 2000, output voltage, output current rating is 500 amp. Now we are asked to calculate the output voltage and current rating in kVA manner for the primary side and secondary side. You see transformer, or motor, we use the rating, we use kVA rather than kilowatt. So kilowatt is not really a good. So you have been kilowatt, right? The watt is weight, the power. In many ways, we try to use kVA because kilowatt will have a power factor issue there. We're not quite sure what kind of power factor in the system. But kVA directly to measure the current and voltage product. That will be more reliable to specify the power. So that's why in many proper systems, we tend to use kVA rather than VA or rather than W. So anyway, so we are asking to calculate kVA rating, and then let's to calculate the current rating in the shared winding M1. So that gives you more information how we understand a transformer. Firstly, the voltage VAB here over VBC here will be turn ratio M3 over M1. So we put a number there, then we found that this turn ratio 200 to 2000, VAB is unknown, then we input is 2000, we can get VAB voltage 200. So this voltage is 200, straightforward, very simple ratio. So that means the output voltage here, just simple summation of voltage, we can get that will be 200 plus 2000, 200 plus 2000. You can have this output voltage equal to 2200 volt. Fair enough. And the next thing is to calculate output power rating. Again, we only care about voltage and current. We don't know power factor here, but that's good enough. So output power rating will be voltage times the current. 1.1 MVA, M means mega, mean 1000. So output power rating here will be 1100 kVA or 1.1 meg VA. And the next thing is to calculate the current conversion. The current conversion is the same as the voltage conversion, just reversed it. So that means the output current and input current ratio, this is a basic equation here. Now putting our own parameter, our symbol here, output current, input current equal to output turn ratio and input turn ratio in here. Just simply put in all the numbers here, then we know that input current equal to 550 amp. Of course, that would be a more ideal analysis. If there's some power losses, or then we may need to increase a little bit of input current. Yeah. Anyway, so the practical input side power rating, of course, with 2000 times current, also 1.1 MVA. So under ideal condition, input-output power rating should be the same, because in this example, we did not calculate any power losses. But however, if in the other scenario, we say efficiency of transformer only about 90%, we need to increase the input power. So that roughly you can use that scenario to understand about the basic parameter about auto transformer. Okay. Third question will be about the power rating. What's the current rating for the shared winding? We are more interested to understand about this shared winding. What is their power like? For any single transformer, we know that input power, output power will be roughly the same or specified by the voltage and current. So we don't really need to calculate. We know output voltage, output current, then we know the power rating is simple enough. But for design engineer point of view, we like to see what kind of power framework on this wire. This is quite interesting. For top wire, not interested because we know the current. Very easy to know what kind of copper we need to use for the top winding for M3. As I said, for M3 winding is equal, this winding equal to output current. So very easy for us, we can know what kind of copper, how thick the copper, the diameter we need to use for the N3 winding. But for common winding here, because current cancellation, if we want to know exactly how much current, we need to do some calculation. We need to, once we do the calculation, we know then we know how to choose the copper, how much diameter for the copper. So now then the calculation here will be this N1 winding, the current will be input minus output current due to the Kirchhoff's law, then become 50 amp. So this current only 50 amp, much smaller than output current. That's a good news. So in theory, I can use much less copper here, very thin wire. That also do. So the contact will be shear winding for much less time. So you can see that output about 500 amp, the shear winding only a small current, mainly due to the phenomenon for the Kirchhoff's law. So that is the that tutorial help you to understand about the current rating, how to design auto transformer, how to make use of proper copper. Don't use many people, they will just using the same copper, top line and bottom line. In the way after the example, you know that you may wasting some copper because you can use less copper in the bottom line. Very simple tutorial, but the implication here will give you more understanding how to design transformer, how to understand the current cancellation. We tend to use more current cancellation in here. We can reduce some power. So it seems that we prefer current cancellation, we can reduce the power loss, but we don't like voltage cancellation. We're wasting the number of turns. So in this slide, we can learn a few things. Transformer can able to cancel some of the number of turns by using different combination. In a way, we can maybe lose out some of the number of turns, lose out some power rating. But in here, we can use current cancellation. In auto transformer, we can reduce the requirement for the copper. So that implication here. Any questions? Good. And then next thing will be like to go to another topic, three-phase transformer. In the market, actually, there are much more three-phase transformer than we expected. Because whenever the power rating is higher, for instance, more than 3 kilowatt or 3 kVA, we tend to use three-phase because too high power, single transformer may not able to do the job properly. So that you show a long high power, we use three-phase. Like, for instance, for the power distribution or overhead line, they use the three-phase. You can see 3 wire there because they need to digital power in three-phase manner in order to provide you with higher power. So here will be a various configuration for three-phase transformer. Three-phase, that means each side input output, we have three-phase. I think you all learn about the transformer, we got delta connection and star connection, right? So the symbol here, star connection, we usually using a symbol called Y because Y look like star. So like in here, we got star to delta, which input will be star, output will be delta, or input can be delta, output can be Y. I think you all learn three-phase, right? So that is one of the configuration. And then, so like this winding, we couple to here. This winding, we couple to the next. And remember the dot rotation. Dot rotation should be in such a way. Don't confuse with dot rotation. Yeah, especially when delta as well, the dot will appear in this sequence. And each of the phase usually different by 120 degrees as usual. And then we can also observe that if the input is equal to V, the phase voltage, this is called the phase winding, or phase voltage equal to V over √3. So we got less voltage in here. And in the output side, depend on the turns ratio in here, then you can see that the output phase voltage actually also equal to the line voltage. And then the current in here, like that, output current will be equal to √3. And then the product in here, this multiplied by this will also give you about the power. Okay. So that's a basic configuration for how a three-phase transformer and also the voltage relationship. But that's also very standard drawing. You can get this from any textbook or any internet. Very simple. But do remember here how we produce the dot rotation. The dot rotation is important when sketch. If I ask you to sketch a three-phase transformer, be careful about this dot will connect in sequence in such a way. And then for the star connection, the dot will be in here. That's the usual connection. In the coupling here, so usually this phase A connect to this phase A, there's a face-to-face connection. Yes,
So what is the difference between the Y delta formations and the delta Y?
you see, when we in three phases, connection method, we can connect in delta or star connection. Like in here, three-phase transform just means we have three separate windings. And then we connect the three separate windings to receive the three-phase voltage from the power distribution capacity. But how to connect them? You can see the combination here. That's a truly common combination. You can connect in star like this way or delta. As I said here, the star connection each winding in here, we have less voltage from the input because two winding share the input voltage. With this two winding, display by 120. So I think you know that this two is not a direct summation, but it's a vector summation. So that's why I'm going to go through here. I think you learned that in three phase. Right? And similarly here, but the delta output will be directly equal to the output. So this phase voltage equal to this 9 voltage.
So I'm not asking for the difference between delta and star, I'm asking for the difference between the two on the left and the two on the right. Like, what is the actual full difference? Is it just the current direction?
This may quite a lot of difference between them. When we configure the transformer connection, you can see the next few slides. We can have star, delta, delta, star, 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 delta, delta. Let the transformer configuration, we have many possible connection methods. So just like when you make up something, you can have different ways to put them together. So these are basic configuration we can foresee, we are able to design. That doesn't mean you have to use this one or that one. But each one of them have their some kind of the phenomenon or feature, make it different application. For instance, you see this winding, we now have two winding share this one. So that will say the voltage rating of this one with less than input. So in a way, we can use less voltage rating copper wire to do the same job. That's one of the advantages. Because high voltage rating for the copper more expensive. But however, in here, then when we connect them in such a way, we now have this winding has to operate on higher voltage. But the current here will be less. High voltage, less current. Then we can use thinner copper.
No.
So that depends how you want to operate your system. If you want high voltage, low voltage. Sometimes some of the motor, we can use delta star connection. You can see that this connection here just mainly how we should put them together. You can use some relay to change the connection from star to delta. So that will say when you initially start a motor, when you start a motor, that's what you can see that I want to start it from safer voltage. Because the input 120 volt. You 120 volt high for winding, actually you have too high voltage, too high current. Then you start the motor from the star connection first. Putting two winding to connect to 120. Then each winding you send for less current. Let the motor to start smoothly first. Once the motor go to high speed, then you change the connection to a delta. Then the motor will more comfortable.
Would you be able to do that with transistors and just?
Yes, that's a really nowadays the star delta connection for the motor is really common. You can do it quite easily. Of course, that is the old technology. That is the thing we learned 30 years ago. But today we are using immersion. We don't have that problem. However, if you don't have inverter, you can still using the star delta connection. We configure the connection to do the same job. Yes.
I'm guessing the three-phase would have more losses than just inverting it to, or like just turning it to DC and then, or getting it down to two-phase and then just using one winding. Or like
As I mentioned, so high power, more than 3 kVA system, we tend to use three phase, even more balanced. You see single phase, same power, then you can see that we are drawing too high current from same kind of the phase winding. That may not be a good design. You don't want that, especially when we have three-phase rectifier. There's a lot of the content here. For instance, if we have a three-phase here, after rectifier become this. If you convert to DC, then you can need to fill up this is quite complicated. You have difficulties to fill up this hole here because single phase. But when you have three phase, then you actually will be doing this, right? You are much easier to fill up all the gap there. So especially because today everything is DC, we don't really use AC anymore. So that means when you operate DC, how are you going to fill up this gap? It's really impossible. Really wasting your energy storage.
I was gonna ask, is in the connection between the Y and the delta forms, is only one of the coils connected to a core that connects to two circuits?
Next few page, you can see how we do the connection.
Okay.
Ready for a few more seconds.
All right.
Then you can see how we put the winding into the next core. So here will be give you some basic configuration about star and delta connection for three-phase transformer. And then here we got other connection, like you mentioned about delta to delta. It's also possible and star to star. So that's very combination, four combination, depending on how you try to work them out. But you can also see that you get this was a low neutral connection. I think for three-phase system, you can see that beside the three-phase, usually for that will be good enough. But for safety and the three-phase voltage go into the building, you tend to create your own neutral voltage. So for instance, when you have the usually the name say L1, say L1, L2, L3 in each of the point here, right? And then this one we call the neutral. So for three-phase system, usually the neutral point will be 0 volt. You don't care about the neutral. In a balanced system, so that means in most of the cross-country or power distribution, we only need 3 wire. But in a way, in many buildings, they will create you the neutral connection. So that will be helping you with some of the power connection and safety. And then for three-phase, you usually go to your house, and your house will mainly using the single phase. So we're tapping the power from here, become L and N, to give you the single phase voltage. But you can see that in your house, many of house, you are either only a single phase, or sometimes you also have three phase. And then each of phase here, they will have different voltage in phase angle. The amplitude is the same, the phase angle is different. So that means in your house, you don't connect two sockets together. You think connect two sockets and double the current. No, don't do that, because they may in different phase, they may different in 120 degrees. So in these two slides, we'll show you the wiring connection, how we put two transformers together. And then for viewing how we put them into a magnetic core, that's one of the configuration. You can see here, and three phase, each will be putting into one of the phase. And then for wiring A, the magnetic first looping in secondary, similarly here, looping here. But each of the first A, B, and C are also displayed by 120 degrees. The same kind of three-phase magnet. Then in a way, you putting 3 equal amplitude and different by 130 degrees. The one in the middle can actually cancel out, become really, really small with negligible thrust. So that's how a three-phase transformer looks like. So that means if the three-phase is balanced exactly, then the first total thrust in the middle will equal to 0. A summation of the three-phase. And then another way to connect them will be like in an E-core, which will be such a way. Again, this is also very commonly being used transformer, three-phase transformer. Each of the lead, you call it lead, about each of the phase. And then this in fact will be also displayed by 120 degrees. And this first, when they come together, they cancel out each other. So there's no actual front by three-phase combination.
What's the actual shape of that transformer? That must be in 120.
Yes, exactly. The each phase angle will be 120. What is the basic three-phase phenomenon? But you can see that P, Q, and D, when they provide you the power, they must be 120 degrees. But the international guideline will be, they only allow you different by a certain percentage. I think no more than 1 degree. That's the international guideline.
Yeah.
Because nothing can be perfectly 120 anyway. So that's why one of the things we can see that. And lastly, before we go away, they see that how many secondary? For this transformer, primary and secondary, they put them on the same kind of magnetic limb. Like in here, the inner winding will be the primary, outer may be secondary, and close to each other. Between them will be some kind of insulation, electrical insulation, to make sure they don't have any short circuit. Under the searching current, they get short circuit. So we have primary, secondary, primary, secondary, and secondary. So that's how we construct a transformer. In the lab, of course, you know how to construct a transformer. So tomorrow then will be left. If anyone has done the lab, then tomorrow we'll show you how to do the winding transformer. Before you go away, any questions? You find this lecture interesting? A simple transformer becomes interesting transformer. Law of the thinking.
Simple.
This was simple. Simple. Then you can have all this combination. But it's still quite interesting. Then you can decide one complex just transform.
Yeah.
That's it. Okay, see you either tomorrow or next Monday. Bye-bye.
It's impossible without the understanding of diagram.